So you were asked to explain why this diagram proves that these two expressions are equivalent. So even if you're not ready, you know, we gotta keep moving. Table 3, can you tell me why? Can you tell me what the diagram contains? Well, if you're not answering why the diagram shows these two expressions, I'm trying to make it easier for you. So can you tell me what the diagram has in it? Two boxes with two different side lengths. What shapes are these? Table 3. And if we have the dimensions of a rectangle, what can we find? Area. So maybe let's try that. See if it leads us to the reason why that these two are equivalent. So if I have a rectangle that's 6 by 3, class, what's the area of that rectangle? 18 units, and we don't know what the units are, but 18 units squared. So 6 times 3 is 18. Then this other box, give me one of the side lengths, but hopefully you know what the other side length is from your critical thinking skills. What's going to be the area of this rectangle? 24. Because if this is a side length of 6, and these two are literally put together, then this also has a side length of 6. Multiply those to get the area, we get 24. Now, if we want the area of the entire shape, you just add those two together. What's 18 plus 24? 42 is correct. Now that shows the same math that's on the right side of that equation. There's another way to get it. If I want the area of the entire shape, and I do have both side lengths here, I could just add these together. What's 3 plus 4? And then I have a large rectangle with dimensions of 6 by 7, which is what when I multiply them? Also 42. So it's a visual diagram of what property did we just do? The distributive property. So maybe also write that in. That's super important. It's making an appearance in this unit. You might already be very familiar with the distributive property, and that's great. I personally have never done a diagram for the distributive property, but I'm more of a left brain person. I'm really good with numbers. You, as a right brain person, might like this visual representation more, and you could do that every time a distributive property problem comes up. But what the distributive property says to do is to take that outside number and multiply it by both terms inside, where they're either like adding or subtracting inside. And it's the same thing as doing A times B plus A times C. And then when it's all numbers, you can see that really clearly. It does give us the same answer. Also, I'll just include when there's subtraction involved in the parentheses to cover all my bases, but mostly we'll just be looking at positive examples today. So now with that same understanding of how this diagram now works, prove that 5 times the sum of x plus 2 equals 5x plus 10. Try that. And because it's Monday and there's not a whole lot of time, I'm going to limit you to 1 minute. So give it your best shot before I call it. Show a new diagram that proves these two are equivalent. Now, to make my life easier, I mean, you could have put it in a different orientation. That's totally fine. But I'll just copy like what I already have. Table 5 if I'm trying to now prove that these two expressions are equivalent using a diagram similar to this one, then what needs to go here where my mouse is? Table 5 is what I was asking. But yes, it does have to be 5. So table 5, what would have to go here now where my mouse is? And table 6, what would have to go here where my mouse is? 2. So you really could have just followed the position that each of these numbers are in. You could have switched the X and the 2 and it'd still be correct. But the 5 has to go here because I need to multiply the 5 by each of the X and the 2 to get the 5X plus 10. So then table 7, what's 5 times X? That's the area of this rectangle. Table 8, 5 times 2.
10.
Good, so that's the area of this one. And if I want to combine those areas to get the full rectangle area, combine means add, it'd be 5X plus 10. The difference with this one and the one from number 1 is that you can't simplify it to one term, like in number 1, because these are not like terms. So the most I could simplify it to is this 2-term expression. Okay, so questions on how the diagrams work. If you already know how the distributive property works, great. But that can help you as you get stuff. So let me briefly read you the goal of today. Yes, when Karen is that one. So we're going to use diagrams to help us rewrite quadratic expressions. What's the minimum requirement for something to be a quadratic expression? So start memorizing what needs to be in the equation for it to be quadratic. Just like how you know the equation for linear and exponential, we need to know this one has what?
That's like X.
An x to the power of 2. It can have other things in it, but as long as the exponent 2 is on an x and there's nothing higher, like not an x cubed, not an x to the 4th, then it's quadratic. It'll make that U shape. So remember that. You'll see that most of these will have x squared or some variation of it. And we're going to rewrite it in different expressions using an area diagram or distributive property. I'm recording right now, just like I do every day. Usually I record in this class, but even if I don't in this class, like I'm always recording at some point. So just, they're always there in case you ever need it. Like I've been getting messages about students being out for excessively long, whether it's for like a good reason or a bad reason, you still have work to be done. You still have lessons to learn. You still take the same tests as everyone else. So you need to catch up on your own time. So there's that. Take notes on your own paper if you need to. Puzzle piece is lesson 8. And you can expect your next quiz to be on Wednesday over these lessons. Any questions? There is Saturday Academy this Saturday. If you have an F in here, and I plan to add my strat points, hopefully I have enough time to do that today before I send out invitations. But if you have an F, you can expect an invitation from me and a message home to your parents about it. Because quite honestly, like if you're not actively trying to get that F up, then you will be here summer school if you pay for it, or next year. Because there's no guarantee that summer school is free. In fact, I heard that it's not. So yeah, that's the 2 options. Get it up now or do the class again. Any questions? All right. And mind you, I mentioned this a bunch of times. There's only 3 unit tests, so that each of them have to be good. Hopefully, if you were in stride today with me, hopefully the corrections we did bump you back up to passing. But otherwise, like then you have to come to tutoring. and you do corrections, and you may be asked if you can do a retake. But that's where we're at. Also, if you remember in the everyday life, Mr. Centeno said something about grade bumps. If you are a ninth grader, which the majority of you are, you take the ACT Aspire, and that is attached to grade bump. You could get a grade bump for math, English, and science, but like assuming you do well on that part. So like there's a math portion. As soon as we're done with unit 6, we're spending like all our time just test prepping for it. And really the score that they want you to get is equivalent to like a 60%. So it's very possible you could get a grade bump, and it applies to both semesters. So say you got an F last semester, you can now get that credit back with the grade bump, even if that F was like a 10%. This ACT Aspire is no joke, like it has grade bumps attached to it. If you got a B, you can get bumped to an A. And same with this semester, whatever you end with will be bumped depending on how you do on that test. So keep that in mind. Still do your best in here, but that's another thing that does matter, like benchmarks do matter. It's prepping for that. All right, but moving on, tangent over. We have other things to do today in 15 minutes now. So applying the distributive property to multiply out the factors of or expand 4 times the sum of x and 2 gives us 4x plus 8. So we know the two expressions are equivalent. We can use a rectangle with side lengths x and 2 and 4 to illustrate the multiplication. So similar to what we did in the warm-up part. You guys will now draw a diagram to show that these two expressions are equivalent. So now we're adding in extra variables, things like that. Don't overthink it. It's still the same procedure. Show that these two are equivalent by making your own diagram. Give me 1 minute before I'm talking. If you're already done with that, you can move on to distributing these, where the diagram is optional, but you still need to be able to distribute. Give you 1 minute on number 1. The diagram to show that these two are equivalent, what would need to go here where my mouse is? All right, table 1, what would have to go here where my mouse is? Table 2, what would have to go here? N. All right, and then what is inside would be our areas. That's what we get from multiplying the dimensions, which is the same thing as applying the distributive property. You have to multiply the outside number by the inside numbers, or use this area diagram. So then table 3, what's 2n times n? It's not. No. Care to venture another guess? It is 2n squared, but even if that part wasn't revealed, what's n times n? Class? Okay, listen, eye contact. N times n. M times m. If you're more than one person, you can do this all day if you need to. X times x. W times w. Not stopping until we want people. A times a.
A squared.
P times p.
P squared.
Okay, so don't forget that fact. Because that's what is really like making this a quadratic expression, the fact that we have a variable squared. The numbers in front are our coefficients, remember that word? You just treat those like normal. So like this is a 1n, because if it's not written, it's one. 1 times 2 is still 2, n times n is n squared. You with me on that? Okay. So then table 3, what's 5 times n? 5n. So there's that. And then when you put it together, you want the area of the whole rectangle, not just those individual parts. It's 2n squared plus 5n, and I can't go any simpler than that because these are not like terms. They're both n's, but one's to the second power, one's to the first power, I guess. Okay, questions on that? If you haven't already, now distribute these. You could make a diagram if you want to, you don't necessarily have to anymore, I'm not forcing you to anymore, but it might help you if you get stuck. So we're distributing in parts A, B, C, and D. I'm giving you no more than 2 minutes because we still have a whole nother part to talk about. Diagram that was optional this time. What you did have to do, no matter what, was distribute. So take the outside number, times it by both of the terms inside. So then table 6, what's 6 times 1/3 n? Okay, while you do that, table 7, what's 6 times 2? And that's positive, so I'll put plus 12 for the second term. You can use a calculator for the first term, but it won't multiply variables for you. If anything, it could just times the 6 by the 1/3. Those are the buttons you would press. So table 6, what's 6 times 1/3 then?
It's 2.
2n. Okay, questions on that? So the calculator could do the numbers for you, but it can't do the timing by variables. If your calculator is doing that, know that that's not one you'd be able to use on a test. You'd have to know that n times n is n squared and whatever. So stick to Desmos or like a real calculator. Yeah. Table 8. What about when I distribute p? What's p times 4p? 4p squared. 4p squared. Table 9, p times 9. Okay, good. P times 9 is 9p, positive, so we'll put plus. Table 1, can you distribute this 5r completely? And then the second term. Okay, good. So you can use the calculator to work out this part. 5 times 3/5 is 3. And then there was an r there still, so plus 3r is correct. This one, the orientation is slightly different, but hopefully you were still able to figure out that you distribute that W. Table 2, can you tell me what we get when we distribute that W? Point 5 W times W. All right, and then W times 7. And that's it. And in none of these, could I combine anything? Because there were no like terms. Like terms would be the same exact variable to the same exponent, and these are not. This is W squared, W to the first. R squared, R to the first. You can't combine. Questions on that? Okay, I need to at least show you the last part, and you kind of fell behind in that. So now we're gonna look at when it's a two-term expression times another two-term expression. So in this situation, it's like at the bottom of your first page. It's x plus 1 times x plus 3. You have a few methods. You could use the area model, where x plus 3 would be this whole side length, and x plus 1 would be that whole side length. And you're finding the area of each individual rectangle. So like, class, what's x times x? Good. What's x times 3? All right, this box has dimensions of 1 by x, so what's 1 times x? 1x. And this one has dimensions of 3 by 1, so what's the area? Now, if I'm showing that this is equivalent to this, and I know that my area of this entire rectangle, I would have to add up like all the smaller areas. Okay, stop packing up, or I won't let you leave until we get through this example without anyone packing up. How did we get from this to this? What did they do? And my like terms are the same variable to the same exponent. So in the middle here, I have 2x to the first powers, which means I can combine these terms. Combine means add, and really it's just referring to the coefficients that you're adding. So 3 plus 1 is 4. And when you combine like terms, you don't change the variable part at all. Everything else doesn't have a like term. It doesn't magically go away. It's still a quadratic function. All right, I encourage you to get the rest of the examples that we did earlier from Schoology. It'll be in there. Otherwise, we're practicing this more tomorrow. So I'm really not that worried.
Well, I'll just be recording me working out these examples, even though my class has now left, because I imagine that the rest of my classes will be able to get through at least these next few examples. So I'll just have them on here for completion of the notes. But the first one that I would show is 2a. And I would show them that you cannot just distribute the exponent. That's not the same thing as raising that to the power of 2. You would have to remember that exponents tell you to multiply the base by itself that many times. So for this one, you have to expand it to this. This is the same as x plus 5 in parentheses squared. And then you could continue to make the diagrams, which if I do, because it says to draw diagrams for this, it would be really similar to the one from number 1. But I would also take this opportunity to show that you could also just look at this as a double distributing, meaning take the first term from the first parentheses, multiply it by both of the terms in the second parentheses, then take the second term, multiply it by the other terms. This is also known as foiling too, first, outer, inner, last, because that happens to be the order that we're multiplying, but I think I'll save the foiling terminology for tomorrow. Anyway, we're multiplying the x by both of the terms in the second parentheses. So x times x is x squared. X times 5 is 5x. Now we're multiplying the 5 by both of the other terms. So I have 5 times x is 5x, and 5 times 5 is 25. Combine like terms. That's how we get that x squared plus 10x plus 25 is equivalent to this expression from 2a. All right, and then I had my students try 2c and 2d. Because in my opinion, I think 2b was a bit easier. We don't need to practice that one as much as we need to do these ones where it's a binomial times a binomial. All right, so if you use either the FOIL method, the double distributing, or the area model, you will get the same answer so long as you do it correctly. So I'll do the double distributing. So I think that makes sense to most students when I call it that. I have 2x times x, which is 2x squared, 2x times 3, which is 6x. Then I have 1 times x, which is 1x, and 1 times 3, which is 3. Combine like terms. That middle term becomes 7x, because 6x plus 1x is 7x. So that's my answer for 2C. For 2D, notice that we have all variables. So I'm taking this first x, timesing it by both of the terms in the other parentheses. X times x is x squared. X times n is xn, or I'm going to put nx because I like the alphabetical order part of it. Then we have m times both of those other terms. M times x is mx. M times n is mn. And there's no like terms in this one. So after that, we are finished.